Hey, welcome. Have you ever stopped to think about your body as, well, a machine? Not just some complex biological thing, but a machine that actually runs on the fundamental laws of physics. Today, we're going to break down exactly how your body uses energy, from just thinking all the way to a full-on sprint. Okay, let's get into it.
So get this. Right now, as you're listening, your brain is devouring almost a fifth of all the energy you're burning, just by sitting there. It is an incredibly power-hungry organ. And the principles that dictate that energy use, they're the same exact ones that keep planets orbiting the sun. It's all connected, and we're about to see how.
And this whole incredibly complex system of energy in your body, it all boils down to one simple, really elegant concept from physics. And that concept is work. Understanding what a physicist really means when they say work is the key that unlocks everything.
First up, let's look at your body's baseline energy budget. What it's burning when you're not even moving. And this is where things get really, really surprising.
So we started with the brain's 19%, which is huge, right? But look at this. The biggest energy hogs in your resting body are your liver and spleen, pulling a whopping 27%. Even your muscles, just sitting there, take a huge slice of the pie. It just goes to show your body is never, ever off. It's always working just to keep you alive. Now, there's a scientific term for all this constant energy burn. It's called your metabolic rate. And that baseline number we just saw, the energy you burn when you're totally at rest, that's your basal metabolic rate, or BMR for short. Think of it as the cost of doing business, the business of living. And it's not small. About 75% of all the calories you burn in a day go just to these basic functions.
So clearly our bodies are doing something to burn all that energy. But to really get it from a physics perspective, we need to get super specific about what work actually is. In everyday life, work could be studying or sitting at a desk, right? But in physics, it's got a razor-sharp definition. Work is only, and I mean only, done when you apply a force to an object and that object actually moves some distance. So if you push against a solid brick wall with all your might, you'll feel exhausted. But if that wall doesn't budge, you've done zero work on it. Tough, but true.
And here's the crucial link. Doing work on something directly changes its energy. And the most obvious change you see is to its energy of motion. I mean, think about a baseball pitcher. They apply a huge force to the ball over the distance of their windup. They do work on the ball, and what's the result? The ball suddenly has a massive amount of motion energy as it flies toward the plate.
Now, this connection between work and energy isn't just some vague idea. Oh no. It is captured in one of the most powerful and fundamental equations in all of physics. It's a universal truth.
Now don't worry, we're not about to turn this into a heady math lesson. But it's worth taking a quick peek under the hood. Physicists didn't just stumble on this. They started with the super formal calculus-based definition of work, plugged in Newton's famous F equals ma, used a couple of clever tricks, and out popped this incredibly simple, beautiful truth. And here it is, the work-energy theorem. It just says that the total or net work done on an object is equal to the change in its kinetic energy. That little triangle, that's the Greek letter delta. In science, it just means change in. So net work equals the change in kinetic energy. Simple, powerful, and as we'll see, totally unbreakable.
And I really want to drive this point home. This isn't just usually true. To quote the folks at Flipping Physics, this always is always true. There are no asterisks, no exceptions. The net work done on an object will always equal its change in kinetic energy, period. Okay. So what is this kinetic energy, or KE? It's just the energy of motion. The formula is 1/2 times the object's mass times its velocity squared. And that squared part is everything. It means if you double your speed, you don't just double your energy, you quadruple it. This is exactly why sprinting feels a million times harder than jogging. That energy cost just skyrockets with speed. But hey, energy of motion isn't the only game in town. What about energy that's just waiting to be used? Well, that brings us to the other side of the coin, potential energy. Potential energy is basically stored energy. It's the energy an object has just because of where it is or how it's shaped. The perfect example, a stretched rubber band. It's not moving, but you know it's packed with energy, just waiting to be released. Or a book held way up high. Its position gives it the potential to start moving. Let's watch this play out. Imagine a rock held at the top of a cliff.
right at the very top, before it's dropped. It's not moving at all. All of its energy is stored up as gravitational potential energy. We usually label that with a U.
Now, as that rock starts to fall, that stored potential energy doesn't just disappear. It transforms. It morphs into the energy of motion, kinetic energy. And right at the halfway point, it's this perfect 50-50 split, half potential, half kinetic. The energy is just changing its form.
And then in that final split second right before impact, the transformation is complete. The rock is at its lowest possible point, so its potential energy is basically zero. All of that stored energy from the top has been converted into kinetic energy, meaning the rock is now moving at its absolute maximum speed. It's beautiful, really. That's energy conservation in action.
Okay, so that was some cool physics. But what does a falling rock have to do with you, your body, and your workout? Let's bring all this physics back home.
So here's a key distinction we have to make. Useful work is the physics we've been talking about, applying a force to an object, like lifting a barbell and moving it. But our bodies also do a ton of what we call internal work. Shivering is the perfect example. Your muscles are firing like crazy, but they're not moving any external object. All that work generates heat to keep you warm. And guess what? Both kinds of work burn energy from the food you eat.
And this table really puts it all into perspective. The energy you consume is measured in power, in this case, watts. And just look at these numbers. Sleeping burns a steady 83 watts, but a full-out sprint, that demands over 2,400 watts of power. That is a nearly 30 times increase in your body's energy consumption rate. It's just wild.
So what does this actually mean for you? Well, let's say you eat an extra 1,000 kilojoules, which is about 240 food calories. Think like a small pastry. To burn that off completely, you'd need to get on a bike and pedal at a pretty good clip for 42 minutes straight. It just shows you how much real physical work is required to burn off even a small amount of extra food energy.
So let's just wrap this all up. At the end of the day, your body is an incredible energy conversion machine. It takes the chemical energy in food and turns it into useful work, into heat, and sometimes into stored fat. This whole amazing process is governed by the unbreakable laws of physics, like the work-energy theorem. And once you realize that every single thing you do costs energy, you start to understand the real science behind diet and exercise.
The laws of energy are the same for everyone, and for everything in the entire universe. But the energy you get from your food every day, that's a limited supply. Which leaves us all with a pretty simple but profound question. Knowing what you know now, how will you choose to use it?